Hi there, everybody. Welcome back to another episode of Chem Complete. I'm Professor Tomney, and we are going to continue our acid and bases lecture today in reference to organic chemistry. So if you have not seen the first lecture portion, I would suggest that you guys go back and check that out. But what we're going to focus on today, when we are dealing with acids and bases, is the definition of what makes something a Lewis acid and a Lewis base by definition. So if you remember last time, we talked about the Arrhenius definition, and we really focused on the Bronsted-Lowry definition. The Lewis definition is going to be the broadest of all definitions, so we can really start classifying most organic compounds as acids or bases based on this definition. It's also going to focus on electrons. So a Lewis acid is any chemical or any substance, so we can put any substance that is going to accept electrons. And this is a little bit reversed because we're used to talking about acids with H+, and the acids give off H+. They donate H+. Well, when we're talking about electrons, Lewis acids would accept electrons. And therefore, a Lewis base is going to be something that will donate electrons. So any substance that will donate electrons. So let me clean that up for a sec. So what does this mean, right? Well, it means, if we take a look at this, that anytime I find something that has a lone pair of electrons, like nitrogen or oxygen or a halogen, so chlorine, fluorine, bromine, anything basically that has lone pairs of electrons, these electrons could potentially allow this compound to act as a base, because those electrons can be donated to something else. So let's take a very, very common example that we could understand, which is H plus as an acid and OH minus as a base. That's about as simple as you can get with acid-base chemistry. Well, the way that this reaction actually works from an electronic standpoint is that the electrons from the oxygen will seek out, and the official word is called attack, but they will go after this proton here. And then what I would form is H2O. And the oxygen would now have 2 pairs of electrons instead of 3, because it donated an extra pair to creating this covalent bond with hydrogen. So let's take a look at that on a bond for bond level, what's happening. So hydrogen just has a proton. That's why we call H plus protons in solution, because they don't have any electrons. So if I were to take a look at OH, I would have a single bond between oxygen and hydrogen. The oxygen is going to have 3 lone pairs to complete its octet. Well, when oxygen is neutral, like it is in H2O, it normally has 2 pairs of electrons that are non-bonding or lone pairs of electrons. So if I have this extra set of electrons here, I have the negative charge present. What's happening is electrons are what we consider to be moving whenever we're dealing with these organic reactions. So it's these electrons that are moving or seeking out the H plus when we're showing this. This is, for those of you that are unaware, this is called a mechanism. Okay, we're going to practice mechanisms plenty as we proceed throughout Organic 1. And you should see them very often in whoever's class you're taking. If you're taking my class, you will certainly be experiencing lots and lots of mechanisms. So what's happening is the oxygen, these electrons are moving over to the hydrogen, and this is going to create a bond here, right? We're going to create a bond. And so this, the OH minus, is donating the electrons, so we would call that the Lewis base, and this would most definitely be the Lewis acid. And these can be considered acids and bases by Arrhenius, Bronsted-Lowry, and Lewis. So this is a very basic example, but we'll take a look at one that's not quite as obvious in a minute here. So what do I end up with? I have the new bond that has formed in order to get water. And now the oxygen that was negative is neutral. And this is another important concept you want to keep track of. If something starts as being negative, okay, so if we start as being negative and you donate electrons, it's going to end as being neutral. Okay, so there will be no charge. If something starts as neutral, so if something starts with no charge, and then it decides to donate electrons, so it's giving the electrons over even though it didn't have excess electrons to start with, it is now positive. Okay, so we'll take a look at this in one of the other examples that's coming up. So let's get a little more advanced. We can take a look at something like HCl and NH3, right? From a Bronsted-Lowry position, this would certainly be the acid, and this would be the base, and that's correct. Okay, we're going to put all our lone pairs in, so make sure we include them for the chlorines if we're doing proper Lewis structures here. So, what ends up happening here? The base is an electron donator, and so an electron donator is going to donate the electrons. Now, a lot of students get confused here, and they think it donates these electrons to the chlorine because the chlorine is electronegative, and therefore it has the, well, when we talk about electronegativity, it has a desire for electrons. Well, its desire for electrons are due to the bond it already has, right? So it's saying that it has a stronger pull on this bond between the H and the Cl. It's not saying that it's going to attract electrons from an outside source necessarily. So what we are going to do here, if you think about this, the nitrogen in NH3 with its lone pair, the nitrogen is partially negative compared to these hydrogens. And so if I have, if I have a partially negative nitrogen and that lone pair is really the largest source of the electron density, the lone pair, which is partially negative, negatives and positives attract. So it's really going to come after the hydrogen or attack the hydrogen. It's not going to go after the chlorine, right? Now there's a problem if I just stop here. In the other situation, the H and the OH came together quite nicely, and we just had H2O. But what's going to be the problem here? Well, if I take a look at this, nitrogen, right, has extended its only lone pair of electrons over to a hydrogen. That's fine. The nitrogen now loses the lone pair. However, I didn't take care of this chlorine. I didn't do anything with it. So as it stands right now, this would be the structure that I'm looking at, and there would be a plus associated with this nitrogen because, again, it was neutral here, and so then it becomes positive if it's losing or donating electrons over to that hydrogen. But the main issue here is we now have a hydrogen that has 2 bonds. This is kind of like a carbon with 5 bonds. We are going past the valence acceptancy or expectancy, we could say, of hydrogen. Hydrogen can only form 1 bond, right? So HCl, if I have H2O, it's 1 hydrogen both going to the oxygen. So it's not that these hydrogens are bonded to one another. Even if it's hydrogen with another hydrogen, looks like that, right? That would be H2. So you have to keep in mind here, we're basically, this is not allowed. This is not a valid Lewis structure. So what do we do about this? Well, as the hydrogen is being picked up by the nitrogen, the chlorine is going to take these electrons because it is electronegative. So the pull that it has on these electrons in this bond are going to basically formally leave and go along with the chlorine. And so what we end up with, and I'll draw this out again in a second, so it's a little bit cleaner. What we're going to end up with is NH4 plus, and you should have Cl minus as the other product that's coming out here. Right? So let's take a clean look at this in terms of what's happening. And that second arrow had to be present because I could not give 2 bonds to hydrogen. Even in an intermediate step, it would still be wrong to show that intermediate and then show the chlorine leaving. The hydrogen at no point in time should have more than 1 bond. And this gets into something that we call transition states. We're going to talk about this later in the semester if you're following along with us. It's not going to be right now. So what do I have going on here? And I'll draw out the bonds explicitly as I'm doing my Lewis structures. So here's my NH3 with my lone pair up there, right? The lone pair comes over and attacks the proton or the hydrogen, and the chlorine leaves, and its extra set of electrons at the end are going to be a result of this bond right here that it's leaving with. So it leaves with that bond, and what I end up with is NH4. Now again, the nitrogen was neutral at first. If something neutral gives up electrons, it becomes positive. Okay, general chemistry concepts. Plus chlorine, which would be negative. Okay, and what would really happen if this was in a solution, these would form some sort of salt, because I have a positive and I have a negative here. However, they need to be shown in these ionic forms. You cannot keep the hydrogen with two bonds. Okay, so hopefully that makes sense. So let's take a look at an even further advanced example. If I have something like boron trifluoride plus, let's say, NCH3, and I've got 3 of them, so trimethylamine is what this would be. Okay. What will I end up with on the other side here? Well, this one can be a little more complicated. So if we take a look at the structures, I've got a nitrogen, and the way that that's written, it means that I've got 3 CH3s. They aren't attached to one another. They're all separate. And on the nitrogen like this, right? And then I would have a lone pair on that nitrogen. Plus, I'm going to end up with the boron, and the boron's going to have fluorine, fluorine, and fluorine. Now, if you look at boron on the periodic table, it's in group 3A. So it can have 6 valence electrons. It can have up to 8, but it normally is going to have 6 when we're dealing with this in its neutral state. And so these fluorines would all have lone pairs as octets, and the boron would exist just how it is, like this. And that boron is going to have a charge associated with it, not a formal charge, but a partial charge. So if you think fluorine is the most electronegative element there is, that's going to definitely make boron the partially positive here. Fluorines can also only bond to one thing, right? So again, if I have HF, or if I have fluoride, double F, like this, the fluorine cannot bond to more than one thing. So I cannot have the fluorine acting as a base here, where I'm saying, okay, the fluorine is going to be attached to the boron, plus I'm going to attach something else to it, like this, right? That's not allowed. Fluorine's going to go past its valency at that point. So that leaves the nitrogen, and nitrogens and oxygens will act like a base very often. You're going to find that, especially nitrogens will. So here, carbon is partially positive. All these carbons are partially positive, and the same thing for the fluorines. These are all partially negative, right? This partially negative nitrogen will be attracted to the partial positive boron here. Okay. And that makes this the acid, because this is accepting electrons, and this is donating the electrons, so that makes this the base. And this brings up an important point. If you have any element as your center atom from group 3A, so what I'm talking about here is the group that has boron, aluminum, gallium, etc., going down the periodic table for 3A, all of these are usually going to make pretty good Lewis acids, right? So for instance, if I had aluminum trichloride, I know this is getting a little crowded here. If I had aluminum trichloride, that would be a good Lewis acid, the aluminum right here. Okay, because they have this partial positive compared to most other things they're bonded up with. So what would I get here? Well, this one's a little bit interesting. The boron accepts the electrons from the nitrogen, so we definitely know that. The nitrogen has the 3 methyl groups because we didn't do anything with them. So if it was neutral and it donated, it's now plus. The boron has accepted those electrons. The boron still has its fluorines, right? We didn't do anything with the fluorines. So the question is, the way I saw before, right, with the HCl, do I have to let go of one of these fluorines for the boron? And the answer is no, because anything in group 2A, which includes boron, can have, it usually has 6 electrons around it most of the time. However, it can have up to 8 electrons, just like carbon, nitrogen, oxygen, etc. And so what we would really do is we would just draw this as a negative positive here. This whole structure overall, because it's a plus and a minus, would not really have a net charge associated with it, but you could have this whole structure in general, okay? And that would be the product there. So that is Lewis acids and bases. Again, just as one more sort of brief summary, you're going to have a Lewis acid that's usually got some source of partial positive, and then you will have a Lewis base. Now, it may be partially negative, it may be formally negative, meaning there's an actual minus charge, but the key here is we're looking for some electrons on the Lewis base, right, that can donate to the Lewis acid in some form or another. And so that's why when we deal with organic chemistry, all of our reactions are going to deal with electron movement. We're going to be pushing electrons to and from different atoms all the time. So you can really frame a lot of these reactions as acid-base reactions. Now, that doesn't mean we always talk about it that way during your course, because throughout your course, you're going to be learning other types of chemistry. It's not all viewed as acid-base chemistry, although it could be viewed as that. So in other words, you're going to come across, and sometimes you may say, oh, well, why are they calling this a substitution reaction and not an acid-base reaction? Well, that just is happening because that's what is best described, to the reaction at the time in terms of what's going on. It still is an acid-base reaction, but it can very often be summarized as a substitution reaction. So you'll get the feel of it as we continue going on. Thanks, and if you have any questions, you're welcome to leave them in the comments section. I will get back to them. I'm working real hard to try to continuously update the channel. I know there's been inconsistencies in the past, so thank you guys for those of you that are subscribed and sticking with me. I will try to be doing content most weekdays if I'm not too busy. And if you like this video, please remember to just let me know. Hit the like button, subscribe if you want to keep up with everything. And I will see you guys for the next lecture. We are going to start talking about organic nomenclature and how to name alkanes, simple organic compounds. So thanks a lot, and I will see you guys for the next lecture.